All right, just as a brief intro to 7.6, I want to go through some of the ideas that direct what we're going to do here. The new material is basically that if I have 3 to the third, I know this is 27, and I write that that's equal to 3 to the x plus 10, okay? Well, the fact is that if this is 27, equals 3 to the x plus 10, and then if I build the logarithm, log base 3 of 27 equals x plus 10, well, this is 3 equals to x plus 10, and then I would subtract the 10 and get negative 7. And that's great, but what I want you to notice right here is that this right here is identical to saying that the exponents in the original problem were equal to each other. That's true specifically because the bases of those exponents are identical. When that happens, and they're set equal like this, we can ignore those bases and go straight for the exponents. That's really the core idea of the first half of the assignment, or the first part at least, is that if we can get the same base to the exponents, then we'll be able to evaluate just the exponents. So when I look at number 10, I see that I've got 10 to the 3x minus 10. Now that 10 looks like it's in its basic form. Over here, though, 1 over 100, it looks like it could be some modification of 10 to some power. And so I want to rewrite this piece as 10 to the, well, 10 to the second would get me 100, and a negative would flip it upside down. So I'm going to say 10 to the negative second, and I'll multiply that by 6x minus 1. That should be equal to 10 to the 3x minus 10. Notice that, like before, I now have the same base for both exponents. So I can ignore those and say that 3x minus 10 is equal to negative 12x plus 2. And to solve, I would add 12x and add 10 to both sides. I'll get 15x equals 12 dividing by 15. X will equal 4 over 5 when I end up reducing. And that's perfect. That's the goal that we're heading for. This is a very, very simple Algebra 1 problem right here. Whoops. Algebra 1. We're in Algebra 2. This is our Algebra 2 step up here. Okay. This idea of changing our base is Algebra 2. This here solving is Algebra 1. So we're using a little bit of our old skills to solve these problems. But that's a pretty straightforward way to handle something like this. As we get into problems like this, I see that x is in the exponent, which means this is an exponential equation. I know that deep down the only way for me to solve this is to go to a logarithm. There are a couple of different ways for me to do that. But first thing I want to do is get as much of this junk away from the exponential piece as I can. So I'm going to minus 1. And have 1/3 times 6 to the negative 4x equals 5, and I'm going to even multiply by 3 to get 6 to the negative 4x equals 15. This is much, much simpler, much cleaner. I notice that I have a base, an exponent, and the result. So I'm going to change this to a logarithm now. Okay? It'd be log base 6 of 15 equals negative 4x. Well, the first thing I want to do is I'm going to evaluate this left-hand side using my calculator and the little thing we like to call change of base. So log of 15 over log of 6. If I do that, and guys, I'd encourage you to keep these things in your calculator all the way through the problem. Try not to round. So I'm going to do log of 15 divided by log of 6. I get approximately 1.511 equals negative 4x. And though I could just use that number and divide by 4, I'm going to keep that in my calculator for using it as an answer. So I'll just divide the answer by negative 4 to get x equals negative 0.378 is what we'll go with. Again, try to stick with 3 decimal places so we can stay consistent. But in generally speaking, you see that it's an exponent, we go to the log. Well, an interesting thing happens that's sort of the opposite of what we did in our first problem. We find that when the bases of logs are identical, and this is base 10 and this is base 10, and they're set equal to each other in this format, there's nothing else besides the logs, that actually both parentheses have to be equal. 12x minus 11 must equal 3x plus 13. And you could think of it as making both of these 10 to the, and we talked about how these would both cancel, and we'd be left with those two equal to each other. We did that in 7.4 with our basic simplifications. So we're going to add 11 and minus 3x to get 9x equals, is it 24? So x will equal, divide both of those by 3, it's 8 over 3. Now it is important to always check to make sure that I do not get a negative or 0 in this parenthesis. If you try sometime, grab your calculator, try to take the log of a negative number. It will not work. And so I need to take this value and plug it in. And I'm just going to check 8/3 is bigger than 1. If I multiply 12 by something bigger than 1, that's going to be bigger still. It ends up being 32 minus 11. That's positive. And this ends up being 24 plus 13. That's again positive. Not too concerned about it then. So this is an acceptable answer. Finally, we're going to look at number 39. And 39 has these two logs on the same side. They do have the same base, but they're not equal to each other. So I can't just cancel the logs. I have to have some other way to solve this problem. And if you remember from 7.5, we know that addition between two identical based logs implies that the insides can be multiplied. So this produces ln of x times x plus 3. So I'm going to distribute, get x squared plus 3x, and say that equals 1. I'm going to remind myself that it's base e. So I can write that e to the 1 power equals x squared plus 3x. Well, I have a quadratic, and quadratics need to be set equal to 0. So I'm going to minus e, which is, minus 2.718. We'll say that. And this equals 0. I'm not going to be able to factor this. I'm going to have to try and use the quadratic formula. So I've got my a, my b, and my c. I'm going to start with negative 3 plus or minus the square root. B squared would be 9 minus 4 times 1 times. And since I'm going to use my calculator for this anyway, I'm going to put an e right there, because it's really e for the c value. All over 2 times 1 is 2. Now I'm going to go ahead and grab my graphing calculator. Whoops. It won't let me do it. Okay. Well, I'll do it on my graphing calculator. You can do it with whatever calculator you have. It really doesn't matter. We're going to evaluate the decimal approximation of the discriminator, this root. So negative 3 plus or minus, and I'll take the square root of parentheses 9 minus 4 times 1 times e, and that e needs an exponent of 1. If you don't have one on there already. Whoops. I'm in trouble. Alright, I'm going to take a pause, and man, I bet you guys already knew what my mistake was. The e is negative. Man, I'm a dummy. Sometimes I make the same mistakes that I see on tests, so I don't think that excuses you from anything. It just means that Mr. Welch is human. Alright, so I'm going to throw that in the calculator with a negative e, and that comes out to be approximately 4.458. We'll use all over 2. Now there are 2 answers here, okay, so I'm going to run through both of them. And if I do the positive version, so I'm just going to negative 3 plus that, divided by 2, comes out to be about 0.729. 0.729. That's good, and if I did the negative version, it'd come out to negative 4.458 divided by 2, about negative 3.729. All right, and if I come right back up to the very, very top, and I try to check these, The positives in here seem to work because adding 3 to something is fine, and then that's positive there. But using that negative 3.7, it's going to end up with a negative 0.729 here and a negative 3.729 here. So that's definitely not accepted. So 0.729 is the acceptable answer. Again, my bad on the negative e, but just kind of quadratic formula takes care of everything for us. Good luck, and we'll see you in class.